So let's begin with our new topic, which is chemical kinetics. Now, this chapter, chemical kinetics, is one of the most important topics of physical chemistry. So, in this chapter, we basically govern with the rate of any reaction. Suppose this is a reaction, say A plus B gives C plus D. Suppose this is any reaction. In this reaction, the A and B are called the reactants and C and D constitute the products. A and B are called the reactants and C and D constitute the products. As time passes, the concentration of reactants decreases and the concentration of products increases. So in a chemical reaction, the concentration of reactants decreases and the concentration of products increases. So this chapter is divided into three topics. First is the rate of reaction. We define the rate of reaction. Right? Second is the integrated rate law. And the last one is the Arrhenius equation. This chapter, chemical kinetics, is divided into these three topics: rate of reaction, integrated rate law, and Arrhenius equation. This rate of reaction is a tool to study this chapter further, and this integrated rate law is the most important section of this chapter. Right? So, let's start with our first tool, which is the rate of reaction. The rate of reaction. Rate of reaction. Rate of reaction means rate of a reaction is equal to the change in concentration by time taken. For example, if the reactants are converted into products, then the change in concentration of the reactants or the change in concentration of the products divided by the time taken will be the rate of reaction. There is something called instantaneous rate of reaction. Instantaneous rate of reaction. Now in this instantaneous rate of reaction, this delta T tends to 0. So it is defined as dC by dt. The change in concentration by time taken where this time tends to 0. This is the instantaneous rate of reaction. That means the rate of reaction at any instant of time. It's defined as dC by dt. Right? Means the change in concentration by time taken. Now, for a reaction, say A moles of A plus B moles of B gives C moles of C plus D moles of D. Suppose this is any reaction: A moles of A plus B moles of B gives C moles of C plus D moles of D, where A, B, C and D, which are in capital letters, are the elements, A and B are the reactants and C and D are the products, and A and B and small c and small d, these represent the number of moles of this reaction. That means number of A moles of A is taken and reacted with B moles of B is forming C moles of C and D moles of D. Right? So this is any reaction, this represents any reaction. In this case, the rate of reaction is defined as minus 1 upon A dA by dt is equal to minus 1 upon B dB by dt is equal to 1 upon C dC by dt is equal to 1 upon D dd by dt. The rate of reaction is defined in this way. For this reaction, A moles of A plus B moles of B gives C moles of C plus D moles of D. The rate of reaction is defined in this way. Right? For the rate of reaction, we only need to know the modulus of the rate of the reaction. We don't need to know whether something is reducing or something is being produced. So we don't need to know the sign of the reaction, sign of the rate of the reaction. So as we know, as time passes, the reactants which are A and B decreases and the products which are C and D are formed. So in this case, the change in concentration by time for A and for B will be a negative quantity. To make it a positive quantity, we multiply with the minus sign here, and we don't multiply with the minus sign in change in concentration by time taken for C and D, because it is itself a positive quantity, because as time passes, the concentration of C and D will increase and the concentration of A and B will decrease as time passes, right? So the rate of reaction is defined in this way. We divide with the coefficient of the coefficient which is the number of moles of A taken. We divide with this because the reaction will proceed according to the stoichiometric coefficients. The reaction proceeds according to the stoichiometric coefficients. So the rate of reaction is defined in this manner, which is minus 1 by A dA by dt, similar in all the cases. And we put a minus sign when we define for the reactants, and we don't put a minus sign when we define for the products, right? This is one way to define the rate of reaction. The second way, there is something called rate law expression. There is something called rate law expression. This is a second way to define the rate of reaction. Something called rate law expression, an important tool to define the rate law expression, to define the rate of reaction. Suppose this is a reaction where A plus B gives products. This is a reaction where A plus B gives products, where products may be anything. A plus B gives products, A and B are the reactants, and A plus B gives products. In this case, the rate of reaction is defined as the rate of reaction is defined as R, which is equal to K into A to the power X into B to the power Y. The rate of reaction is defined in this manner. This was the first way to define the rate of reaction in terms of the coefficients. This is the second way to define the rate of reaction in terms of the rate constant. This R is called the rate of reaction. This K is called the rate constant of the reaction. Rate constant. There is something called rate constant of reaction. Right? This box A is the concentration. It's the concentration of A in molarity. Concentration of A in molarity, and box B is the concentration of B in molarity. Right? And X is the order of reaction with respect to A, and Y is the order of reaction with respect to B, right? Where X plus Y is equal to the overall order of reaction. I will explain. See, this is a different kind of expression which is called the rate law expression to define the rate of any reaction where A plus B gives products. This R equal to K to the power X, B to the power Y, where this X and Y are variables. This X is the order of reaction with respect to A. This Y is the order of reaction with respect to B. This K is the rate constant of the reaction. This R is the rate of reaction. Box A is concentration of A in molarity. Similarly, box B is concentration of B in molarity. And X plus Y, adding these two powers, X plus Y gives the overall order of reaction. Now, let's understand the two terms, which is order of reaction and molarity. Let's first see what these two terms are. The order of reaction and molarity. First, molarity. Molarity is a tool to define concentration. It's a tool to define concentration which is equal to number of moles of solute upon volume of solution upon volume of solution in liters. Number of moles of solute upon volume of solution in liter. This is the definition of molarity. In this chapter, we define concentration in terms of molarity everywhere, which is defined as, molarity is defined as number of moles of solute upon volume of solution in liter. Right? And the next thing is order of reaction. What does order of reaction means? Order of reaction. Order of reaction. Firstly, order of reaction, we should know that the order of reaction is an experimental parameter, Order of reaction is an experimental parameter. It's an experimental parameter. This power x and y we can get only by performing experiments. It's an experimental parameter. There is no other way out to get the values of this x and y. Now, let's understand. Suppose there is a reaction in which A gives products. Suppose it is reaction in which A gives products. Right? In this reaction, we can write the rate law expression as R equal to K into A to the power n. This n is nothing but this x. This n is the order of reaction. The rate law expression as defined here is written as R equal to K to the power n. In this case, where A gives products and in A plus B gives products, it is defined as R equal to K to the power x and B to the power y. Where this x is the order of reaction with respect to A, y is the order of reaction with respect to B, and n is the order of reaction with respect to A. Now, how we check this order of reaction, that is the value of this n. Suppose we have a reaction mixture, In the reaction mixture, let's say if we double the concentration of A, and if we see that the rate of reaction becomes 4 times, that means if we double the concentration of A, and we see that the rate of reaction becomes 4 times, which is 4R, then we can say that this n is equal to 2. Right? If we square it, we get 4 out here. Right? Because K is a constant, so it depends only on the concentration. So if we double the concentration of A and see that the rate of reaction is 4 times, then we can say that the order of reaction with respect to A is 2. Now, in another case, let's say if we double the concentration of A and we see that the rate of reaction is not changing, it's a constant. So then we can say that R is equal to K into A to the power 0. What I am saying is, if we double the concentration of A and see that the rate of reaction is not changing, that means it's independent of A and it's only dependent on K. That means the power will be 0. Right? Anything to the power 0 is 1, so it will be R equal to K only. Similarly, if we see that if we say example, if we triple the concentration of A, and see that the rate also becomes 3 times, if we triple the concentration of A and we see that the rate also becomes 3 times, then surely the power will be 1. Right? So in this case, the order of reaction with respect to A will be 1. Right? So in this way, we define the order of reaction. We change the concentration of the reactant, and check with what value the rate of the reaction is changing. Right? So it's dependent on the concentration of A. And if it's independent of concentration of A, then the order of reaction will be 0. Right? This was the 2 definitions of rate of reaction. This was the rate law expression, and this was the order of reaction, and this was molarity. Right? Based upon this order of reaction, we have 4 types of reaction. Actually, we have n types of reaction, out of which we have only 4 types of main reactions. Say for example, if R equal to K, A to the power 0, then it is called a 0 order kinetics. Then the reaction follows 0 order kinetics. We say that the reaction follows 0 order kinetics. Suppose R is equal to K into A to the power 1, then the reaction follows first order kinetics. Let's say if R equal to K into a to the power 2, then the reaction follows second order kinetics. Second order kinetics. And so on. If I say that R equal to K, a to the power n, where n is the order of reaction with respect to A, this reaction follows nth order kinetics. This is nth order kinetics. We say that the reaction follows nth order kinetics. Right? So in this way, the kinetics of the reaction is defined. We change the concentration of A and we observe the change in the rate of reaction, and by seeing this we define the order of reaction, and in this way we define the kinetics of the reaction. Right? So basically we will study the general cases of these four types of kinetics. Right? So now let's move back again. We define the rate of reaction as the change in concentration by time taken. The change in concentration by time taken. So, if you need to know the unit of rate of reaction, we can simply say that it's molarity upon time. As I told that the concentration we are measuring in molarity, in terms of molarity, which is number of moles by volume of solution in liter, which is equal to number of moles, liter inverse and also time inverse. This will be molarity by time, so it will be mole per liter, so mole, liter to the power minus 1 and time to the power minus 1. This is the unit for the rate of reaction. This is the unit of rate of reaction. Now, our next job is to get the unit of rate constant of the reaction. Unit of rate constant. You know the unit of rate. Now we will get to know the unit of rate constant of the reaction. Rate constant of reaction. Now we do this by using the second definition of, which is the rate law expression. This is R is equal to K, a to the power 6 an nth order reaction. Let's see in a general case. Dividing it, we get K is equal to R upon a to the power n. We get K equal to R upon a to the power n. So we know the unit of rate of reaction, which is mole liter inverse time inverse, which is equal to mole liter inverse time inverse upon, this is molarity again, so it is mole to the power n into liter to the power minus n. Right? Molarity by mole per liter is molarity, mole to the power n, and liter will be upwards, so bringing it downwards we get liter to the power minus n. Right? Making it more simpler, we get it as mole to the power 1 minus n into liter to the power n minus 1 into time to the power minus 1. Right? This is the unit of rate constant of the reaction, and this is the unit of rate of the reaction. Right? So we saw two definitions. First was for the rate of reaction and then the rate law expression, and we saw the unit of rate of reaction and then we saw the unit of rate constant of the reaction. Right? So note where this n is the order of reaction. This n is the order of reaction which I defined earlier. This n is the order of reaction. Right? So now let's see the unit of rate constant for different orders of reaction. Let's see the unit of rate constant for the zero order reaction. For zero order, K is equal to mole. Putting 0 out here, we get mole liter to the power minus 1 and time to the power minus 1. For zero order kinetics, the unit of this rate constant is mole liter to the power minus 1 time to the power minus 1. For first order, it's equal to, K is equal to time to the power minus 1. Right? Time to the power minus 1. 1 minus 1 is 0, n minus 1 is 0 by putting 1 out here. For the second order reaction, this K is equal to mole to the power minus 1, liter to the power 1 and time to the power minus 1. right? So in this way, we get the unit of rate constant for different orders of reaction, for 0 order, for first order and for second order. Now note, for the first order reaction, the unit of rate constant is independent of molarity. It's only dependent on time inverse. So in questions, we will not be given that the reaction is of first order or second order. Many times we will be given the unit of rate constant of the reaction, and from here we will have to identify whether this reaction is of first order, second order, or a 0 order, right? If they say that the unit of rate constant is 10 to the power minus 1, then we need to understand that they say that the reaction is of first order in this way, right? Now, our first part, which was the rate of reaction, is finished. Now let's take up the second part, which is the integrated rate law. We will use this tool. This rate of reaction will be used as a tool for getting the theory of integrated rate law. Now, integrated rate law is the important part, is the most important part of this chapter. So now, let's start with the integrated rate law. Integrated rate law. As I told, this is the most important part of this chapter. Now, our task will be to derive results. Derive two main results. First is the relation between concentration and time, and the next is results for half-life period. Right? We'll be deriving these two results. Now, before proceeding, we should be knowing two important formulas of integration. The first is integral of dx upon x is equal to ln x. Integral of dx upon x is equal to ln x. And the next is integral of x to the power n dx is equal to x to the power n plus 1 upon n plus 1. We need to know these two formulas of integration. Right? These two formulas of integration. Now, someone can argue to use this formula in this case. I mean to say that someone can write this as x to the power minus 1 dx, and now taking n as minus 1, someone can use this formula here and write it as x to the power minus 1 plus 1 upon minus 1 plus 1 will be 1 by 0, which is not defined. Right? It will be not defined. So this formula is not applicable for n equal to minus 1. Right? For dx by x equal to ln x, this will be used, and for x to the power n, where n is not equal to minus 1, this formula will be used. Right? So knowing these two formulas, we'll be deriving these two results for the three different kinds of kinetics: 0, first and second order kinetics. Right? And we will also generalize it for nth order kinetics. Right? So let's begin. Let's begin with the most important order of kinetics, which is the first order kinetics. Most of the questions in examinations appear from first order kinetics. So let's begin with that. First order kinetics. First order kinetics. As we have completed the rate of reaction, we can simply write the rate law expression for first order kinetics, which will be looking like R equal to K into concentration of A, power is 1. And by the first definition, if you take a reaction called A gives product, if you take this simplest reaction, A gives products, and we define rate in this reaction will be defined as minus 1 upon 1 into dA upon dt as the Number of moles of A is 1. So it can be written as minus dA upon dt. The rate can be defined in this way for this simplest reaction A gives products. Using this here, we can replace R by minus dA by dt. Right? We can replace R by minus dA by dt using the definition of rate of reaction. So by replacing we get minus dA by dt is equal to K into A. Right? Now we shift box A here and dt there so that we can get similar terms for integrating. So we can write it as dA upon A is equal to, this box means concentration, this box means concentrations, concentration of A. dA upon A is equal to minus K dt. It can be written in this way, minus K dt. We take minus sign here and K dt. Now, integrating on both sides, limits from 0 to t. At time 0, let the concentration of A be A naught. At time 0, let the concentration of A be A naught, and at time t, the concentration of A be AT. Right? Now integrating we get ln AT minus ln A naught after putting the limits. Ln AT minus ln A naught is equal to minus KT after integration. Or using the property of log, we can write it as ln AT by A naught is equal to minus KT, using the property of log which says log A minus log B, log A minus log B is equal to log A minus log B is equal to log A upon T. Using this property of log, I can write it as ln AT by A naught is equal to minus KT. Or I can write, taking anti-log on both sides, I can write AT is equal to, I can write AT upon A naught is equal to e to the power minus KT, or I can even write that AT is equal to A naught into e to the power minus KT. AT is equal to A naught into e to the power minus KT. Right? This is the first result, which is the relation between the concentration at time t with time using the initial concentration of A at time t equal to 0. Right? Now, for the second order kinetics, for the second order kinetics, we do the we use the similar procedure. We write R equal to K into e to the power 2 for second order kinetics, or replacing this we get minus d upon dt is equal to K e to the power 2. Right? Bringing similar terms on one side, I get d upon A square is equal to minus K dt. Now integrating on both sides from interval 0 to t and from initial concentration A naught at time t equal to 0 to concentration at time t which is AT. Right? Which is AT. Or I can write it as a to the power 2, so it can be written as integration of d upon A square is equal to integration of A to the power minus 2 dA. Right? Using the second formula, I can write it as A to the power minus 2 plus 1 upon minus 2 plus 1. So it will be like minus 1 upon A. It will be minus 1 upon A. Right? So it will be like, after putting the limits, I will get minus 1 upon AT minus 1 upon A naught is equal to minus KT. Right? We put the limits and we subtract the final limit minus the lower limit, and we subtract minus 1 by AT, which is the integration value, putting the limits AT and A naught and putting a minus sign in between, we get this. Now solving further, I get minus 1 upon AT plus 1 upon A naught is equal to minus KT. Right? Making it more sober, I can write it as 1 upon AT is equal to 1 upon A naught plus KT. Right? This is the relation between the concentration at time t with t using the initial concentration at t equal to 0, which is A naught. Right? So we derived two results for the first order kinetics. For the first order kinetics, AT is equal to A naught into e to the power minus KT. For the second order kinetics, we derived 1 upon AT. 1 upon AT is equal to 1 upon A naught plus KT. Now let's check for the zero order kinetics. For the zero order kinetics, using the similar procedure, we solve for the zero order kinetics. R is equal to K a to the power 0, R equal to K a to the power 0, or I can write it as R is equal to K simply, right? Or I can replace it as minus dA upon dt, which is equal to K. Using this, minus dA by dt is equal to K, or I can write it as dA is equal to minus K dt. dA is equal to minus K dt, and integrating on both sides from 0 to t and from initial concentration A naught at time t equal to 0 to final concentration AT. I get it as AT minus A naught using the second formula, that is integrating of dx, and it can be written as integrating x to the power 0 dx, which is equal to x to the power 0 plus 1 upon 0 plus 1, which is equal to x. Using this second formula, I can write it as AT minus A naught, and after putting the limits, AT minus A naught and subtracting, AT minus A naught is equal to minus KT, or I can write it as AT is equal to A naught minus KT. This is for the zero order reaction. This is the relation between the concentration at time t with t using the initial concentration and the rate constant. So this is for the zero order reaction. Right? For the zero order reaction, it's AT is equal to A naught minus KT. Right? Now this derivation is very important to understand. Without knowing this, we will not be able to solve problems. Else we will have to memorize these results. And even if you memorize, there is a chance of forgetting these results. So we need to know this method to derive these results. It's very easy. We just write R equal to. Now let's check it for an nth order reaction. Let's see if we can derive for an nth order reaction. Let's see if we can derive these results for an nth order reaction. Right? Let's see. R is equal to K a to the power n. Proceeding similarly, I can replace R by minus dA by dt is equal to K a to the power n. Right? Doing the same thing, bringing this term down, I can write it as dA upon a to the power n is equal to minus K dt. Now integrating on both sides from 0 to t, from concentration A naught to AT, I can write it as a to the power minus n plus 1, a to the power minus n plus 1 upon minus n plus 1, and the limit will be from A naught to AT is equal to minus KT. I can even replace it as 1 minus a to the power n minus 1 into 1 minus n. Right? I brought it down and take the inverse of minus n plus 1, which is n minus 1, from AT to A naught, from A naught to AT is equal to minus KT, right? Now, I can write it as, if I put the limits, I get as 1 upon AT to the power n minus 1 into 1 minus n into 1 minus n minus 1 upon 1 minus n into A naught to the power n minus 1 is equal to minus KT is equal to minus KT. Now, if I try to make it more simpler, I hope this is clear, right? D upon e to the power n, taking it upwards, e to the power minus n, using the second formula minus n plus 1 upon minus n plus 1, and here minus KT. So, bringing it down again, 1 upon e to the power n minus 1, minus n plus 1, inverse of minus n plus 1 is n minus 1, into 1 minus n, minus n plus 1 can be written as 1 minus n, and now putting the limits, I get 1 upon AT to the power n minus 1 multiplied by 1 minus n, which is 1 minus n, and subtracting with this, we get this. Now, if I try to make it more simpler, if I try to make it more simpler, I can do one thing. I can take minus common from both the sides. I can take minus common from both the sides, and I can make it plus, and I can reverse this. I can reverse this. This will become n minus 1, and this will also become n minus 1. I change the minus sign to plus here, and I change the sign here also, right? So, I can write it in a more general form, like 1 by AT to the power, 1 by AT to the power n minus 1, 1 by AT to the power n minus 1 into n minus 1, right? 1 by n minus 1 AT to the power n minus 1 is equal to, taking this on that side, I get 1 by n minus 1 into A naught to the power n minus 1 plus KT. This is the general expression. This is the general expression where n is the order of reaction, right? Putting the value of n as 1, we get this result. Putting 2, we get this result, and putting 0, we get this result. One thing, this expression is not valid for n equal to 1. N is not equal to 1 in this case, because if we put n equal to 1, we get undefined results. So for n equal to 1, we cannot use this result directly. For any other dam order, we can use this result, right? For any other case, we can use this general result, right? It's 1 upon n minus 1 into a to the power n minus 1 is equal to 1 upon n minus 1 a naught to the power n minus 1, where it is the concentration at time t, and a naught is the initial concentration at time t equal to 0, and k is the rate constant of the reaction, and n is the order of the reaction, right? We took a minus sign common here, we converted it into plus, and take a minus common here and converted 1 minus n into n minus 1, 1 minus n into n minus 1 to make things simpler, to make things similar, right? So this was the general expression. This is for first order, second order, zero order. The maximum priority for appearing questions in exam will be of first order, next the zero order, and then the second order at some times, right? Now, our first wish was to derive the relation between concentration and time. Now our second wish is to derive the results for the half-life period. Derive the results for the half-life period. There is something called half-life period. Half-life period. It's an interesting concept, half-life period. An interesting concept. Half-life period means, suppose there is 4 bacteria. There is 4 bacteria. After some time t, it converts into 8, and after some time t, it converts into 16, right? Then this time t will be known as the half-life period. Understand? After some time t, this breaks into half of its original value. It divides into half of its original value. It's 8, and after some time it breaks into 16. Then if this time and this time is same, then it will call the half-life period, right? Making it more simpler, if I say that half-life period, if I define half-life period, I will say that half-life period is the time taken, it's the time taken to reduce a substance into its half, right? If a substance is of 100% content, then to become it 50%, the time taken will be a half-life period, right? Again, from 50%, the time taken to become 25% will be a half-life period. Again, from 25%, the time taken to become 12.5% will be a half-life period, right? It means the time taken to reduce the concentration of a substance into its half of that value will be termed as the half-life period, right? So we need to derive results, we need to derive formulas for the half-life period for zero order kinetics, first order kinetics and second order kinetics. So what we can do is, in these results, if we substitute A0 by 2 in place of AT, then this time T will be the half-life period, right? A0 is the initial concentration. If I put A0 by 2 in place of AT, then for sure this will be the half-life period time, right? So doing this for first order, I get A0 by 2 is equal to A0 e to the power minus KT half, because this time is the only half-life period when the concentration will become A0 by 2. When the concentration becomes A0 by 2, then that time will be referred to as the half-life period, right? Or it can be written as 1 by 2 is equal to e to the power minus KT half. Or if I take ln on both sides, it will be like ln 1 by 2 is equal to minus KT half, right? Minus KT half. If I explain this, I am taking ln on both sides. So taking ln here, I can write it as ln e to the power minus KT half, using the property of log, which is log a to the power x is equal to x log a. Using this property, I am bringing the power here, I am bringing the power out here, and it is as minus KT half ln e. And when we are using ln, it means the base is e, and ln e to the base e is 1. So it's like minus KT half only, right? Using this, using ln on both sides and bringing the power outside, ln e upon e is 1. Using this concept, I can write it directly. Now, using another property of log, which is log a minus log b is equal to log a by b. Using this property, I can write ln 1 minus ln 2 is equal to minus KT half. Ln 1 minus ln 2 is equal to, and ln 1 is equal to 0, because I say ln 1 is equal to 0 because e to the power 0 is equal to 1, right? Ln 1 to the base e is equal to 0, or log 1 to the base 10 is also equal to 0, because anything to the power 0 is equal to 1. So ln 1 is equal to 0, which is equal to minus ln 2 is equal to minus KT half, or I can say that T half is equal to 0.693 upon K. The value of ln 2 is 0.693, so T half is equal to 0.693 by K, right? So we got the value of T half for first order kinetics, and we see that the value of T half is independent of the initial concentration. In the first order reaction, the value of T half is independent of initial concentration. So if in the question it says that for a reaction the value of T half is independent of the initial concentration, then we need to understand that it is a first order reaction, right? For T half, first order reaction, it's T half is equal to 0.693 by K, right? Now, for the zero order kinetics, using this expression, AT is equal to A0 minus KT. AT is equal to A0 minus KT. Similarly, we replace AT by A0 by 2 and T by T half. it's A naught by 2 is equal to A naught minus K T half. This will be T half when the concentration becomes A naught by 2. Or I can write it as A naught by 2 is equal to KT half. Bringing this term here, it will be a positive, and A naught minus A naught by 2, it will be A naught by 2. So A naught by 2 is equal to KT half, or I can write T half as A naught upon 2K. So I got the value of T half for 0 order also, which is T half is equal to A naught by 2K, right? Similarly, we proceed for the second order reaction. Similarly, we replace AT by A naught by 2 here and T as T half. We write for second order I can write 2 upon A naught is equal to 1 upon A naught plus KT. I replace AT by A naught by 2. So 2 goes upside. So 2 upon A naught is equal to 1 by A naught plus KT, or taking this term here I can write it as 1 upon A naught is equal to KT half. I replace T by T half because this will be the only half-life period when the concentration changes to half of its initial value. So 1 by A naught is equal to KT half, or I say T half is equal to 1 upon Ka naught. T half is equal to 1 upon Ka naught. So this is the value of half-life period for the second order reaction. So for the second order reaction, T half is equal to 1 upon Ka naught. 1 upon Ka naught. Right? So these were the results for the relation between concentration with time, and these were the formulas to know the half-life period time, right? So using the integrated rate law, and using the integration formulas, the basic integration formulas, we derive these two important results, right? This governs the entire chapter, and most of the questions appear on this part, right? And we need to know, using the units of half-life period and using the units of rate of the reaction, we need to know the order of the reaction, right? Many times it will not be given directly in the question that whether it's a zero order reaction or it's a first order reaction, right? And most of the questions appear on the first order reaction, and the next priority will be the zero order reaction, and the last will be the second order reaction, right? So with this, our second part, which is the integrated rate law, is completed, and now we are left with the last part, which is the Arrhenius equation. The last part, which is the Arrhenius equation, right? Throughout the chapter, we discussed about everything except the rate constant of the reaction. We did not discuss much about the rate constant of the reaction. I only told that the rate constant of the reaction is only dependent on temperature, and with increasing temperature, the value of rate constant increases. Now, Arrhenius equation. Arrhenius equation. Arrhenius found a relation between the rate constant and time. He found the relation between rate constant and time, which is K equal to A e to the power minus EA upon RT. This was the relation which Arrhenius found out or derived. K equal to A e to the power minus A by RT, where K is the rate constant. K is the rate constant which we are using throughout the chapter. By now, K is the rate constant, A is the Arrhenius parameter. It's the Arrhenius parameter on the pre-exponential factor. Arrhenius parameter, right? And EA is the activation energy. EA is the activation energy. It's the activation energy, right? And R is the universal gas constant. Universal gas constant, we know about it. R is the universal gas constant, and T is the temperature. T is the temperature, right? Arrhenius said that we know all the chemical reactions proceed. Suppose this is a reaction A plus B giving products. We know the reason of forming it into products. Any reaction proceeds due to collisions. Any reaction proceeds due to collisions. In the reaction mixture, collision occurs, and the products are formed. Arrhenius conceptualized that not all collisions can form products. He conceptualized that not all collisions can form products. Not all collisions can form products. Right? He conceptualized the collisions after which the reactants get the activation energy. Only those collisions form products. The collisions which provide activation energy. The collisions which provide activation energy form products. The collision which provides activation energy form products. Right? Now, what is this activation energy? This activation energy, it's the minimum energy barrier. Activation energy is the minimum energy barrier for the reactants to attain the transition state. I will conceptualize the activation energy and the transition state using graphs, using the energy profile diagram. There is a diagram called the energy profile diagram. This is a energy profile diagram. This is the energy profile diagram. These are our reaction coordinates. Reaction coordinate is known as the reaction coordinate, and this is the energy. This is the energy axis, and this is the reaction coordinate. Let's say this is the energy of the reactants initially, and let's say this is the energy of the products initially. Right? The reaction follows a process governing this path, governing a path like this. Right? Now, in this case, this energy barrier is called the activation energy. This is called the activation energy. Right? This is the activation energy. The minimum energy barrier, this is the energy barrier, and this is called the transition state. Right? At this state, the reactants start converting into products. So this is called the transition state, and the minimum energy barrier required for the reactants to reach the transition state and start forming products is called the activation energy. Right? This is the activation energy. And Arrhenius conceptualized that not all collisions can form products. Right? All the collisions cannot reach this transition state. The collisions which can reach this transition state, which can provide that energy barrier, which can overcome that energy barrier, only those collisions can form products. Right? Using this concept, he conceptualized his equation, which is K equal to A e to the power minus A by RT. Right? Where this A is the pre-exponential factor. Pre-exponential factor. Right? This means the number of colliding molecules, or simply I can say that this represents the number of successful collisions, which can form products or which can attain the transition state. Right? A denotes the number of successful collisions or pre-exponential factor or the Arrhenius parameter. It means the number of successful collisions to attain the transition state. This K is the rate constant, which is a dependent quantity on temperature. It is dependent on temperature. With this equation, it is dependent on temperature. As time changes, K changes. As T increases, K also increases. Right? Now, the last concept of this chapter, using the Arrhenius equation, the last and the important concept and important derivation using the Arrhenius equation, we know K equal to A e to the power minus EA by RT, where this EA is the activation energy. Right? the minimum energy barrier to attain the transition state to form the products. K equal to e to the power minus A by RT. Now, we know that it is a dependent quantity. The rate constant depends on temperature. Now let's say we have two temperatures, T1 and T2. And let's say we know the value of rate constant at temperature T1, which is equal to K1. And if we need to find out the value of rate constant at temperature T2, then for this we will be deriving a general result so that we can answer this, right? So what we do is, we make two equations. K1 is equal to A e to the power minus E upon R T1. At temperature T1 the rate constant is K1. Similarly at temperature T2 the rate constant is K2. K2 is equal to A to the power minus A by R T2. We have these two equations, and what we do is, we take anti-log on both sides, we take log on both sides and subtract equation 1 and equation 2, and we get a result called log K2 by K1 is equal to minus E upon 2.303 R into 1 by T1 minus 1 by T2, right? Or it can be written as log K2 by K1, log K2 by K1 is equal to minus E upon 2.303 R into T2 minus T1 upon T1 T2, where this T2 is greater than T1. This T2 is greater than T1, right? So this is the last concept of this chapter, right? What we do is, we took log on both sides, and after taking log on both sides, we subtracted equation 1 and equation 2, and we get something like log K2 minus log K1, and using again the formula of log, which is log A minus log B is equal to log A by B. Using this, we wrote it as log K2 by K1, and we got a 2.303 here because for converting log x into log x, we need to multiply it by 2.303, right? Log x to the base e is equal to 2.303 log x to the base 10, right? For converting it into log, we multiplied it with 2.303, right? And the rest expressions will get it easier when we subtract it, right? So this is one of the most important formulas. It is used in questions, and questions appear of this type where we know the temperature 1, temperature 2, and we know the K1, and we need to find K2, right? Right? So this is an important formula, and till now, whatever formulas we derive, questions may appear in this way that we need to mix two things. For example, if we know this formula as T half is equal to 0.693 by K, and if I know this formula, which is log K2 by K1 is equal to minus E upon 2.303 R into T2 minus T1 upon T1 T2, right? Questions may be framed in this manner that we need to solve K2 from here, and we need to put K2 out here, and we need to get this T half, right? So whatever equations we have derived, we will have to mix them while solving questions, right? So this was the theory for this chapter, Chemical Kinetics, and you may now give your hands on the problem solving, right? You may start problem solving, right? This was the complete theory of Chemical Kinetics. So, thank you.